Welcome! This lecture about classes and objects is in many ways the heart of this course. There's a lot in this lecture, so even more than usual, remember the option to pause the video if you need to have a quick think about something. There are a few places where I will strongly encourage you to do so, but you can do so in other places too. We said a little bit about why object orientation, but now it's time to say a bit more. And although this course is a programming course, not a software engineering course, we have now to talk about software engineering because this is the fundamental reason why object orientation proves successful as a programming paradigm. It's because it turns out to be particularly adept at managing change, which is what software engineering is all about. The thing that's sometimes quite hard to get a grip on when you first start programming is that the difficult thing is not so much writing the program in the first place, it's changing it when something about the environment in which the program has to exist changes, whether that's something technical or something about the user's requirements. And such change is absolutely inevitable. It is much more important as part of the total cost of ownership of software than the cost of developing the software in the first place. Things change all the time, the world changes, and therefore it's really important to have a collection of tools and languages that make it as easy and cheap as it can be to make changes to your software reliably. So how do we go about making it easy and cheap to change existing code? Well, one of the things we must obviously do is try to minimize the amount of code that must change. We would like to be able to make the most common changes by changing only a few lines of the code rather than hundreds or thousands of lines. Slightly less obvious perhaps is it's important to make it easy to work out which code must change. So it might be that you have 5 lines of your million-line program that must change. It's much easier if it's 5 adjacent lines than if it's 5 different lines in different parts of your program. And what this says is that we would like a programming language and a set of tools and a way of building software that, as much as possible, makes sure that code that has to change together will live together in our body of source code. And this turns out to be something that object orientation is quite good at, which is really, I think, the major part of the explanation for its success. Related to this, in a way that may not be completely obvious at this stage, but stay with me, is the idea of information hiding. And what we mean by this is that we try to limit the amount of information that somebody who wants to use a piece of code needs to know. So we hide certain information inside a well-defined piece of code, and the idea is that the hidden information is intended to be information that a user of the code doesn't need to know about. Now, doesn't need to know about means a bunch of different things. It means it's safe to use the code without knowing the details that are hidden. It also means that the code that somebody writes that uses your piece of code will not depend on that hidden piece of information, and therefore will not need to change if part of the hidden information changes. And this is the fundamental idea of modularity and abstraction. You've already seen this to some extent via functions, so you've seen the idea that you can write a piece of code which is the body of a function. You can give the function a well-chosen name, and then somebody can call that function, and the idea is that they shouldn't need to know all the details of precisely what happens when they call that function. They should be able to trust that you've chosen a good name, and perhaps you've documented it well, perhaps you've even written a contract for it, such that that's all they need to know. Okay? Now that idea is applicable much more generally, and in particular in object orientation it's applicable at the level of classes and objects. Let's go up a level again for a moment though and think about application programming interfaces. Now APIs, I'm sure you've come across this term in various places. This is just the name for whatever interface you have between the user of the code and the implementation itself. The API is the kind of negotiated protocol for communication between the implementation programmer and the application programmer who is going to use our implementation. This idea, of course, did not originate with software, and it's applicable much more generally. And here's an example using a hardware interface. When you have a client who is going to interact with a device such as a television, the client does not, of course, have to understand how the television works or even what hardware is actually present inside the television. What they need to be able to do is to use it. And we have a well-established API for using a television in the form of a remote control. And the remote control allows you to do things like adjusting the volume, switching the channel, switching to standby, and so on. And so the client needs to know how to use that API, and the implementation needs to know what API it's supposed to implement. So because the API is functioning as the interface between the implementation and the implementation and the client need to agree on the API ahead of time, and then they can do their separate development, both of them relying on that API, and neither of them needing to know the details of what the other is going to do. That's my son, by the way, quite a few years ago now. And one of the things that this means you can do is that it's possible to substitute a better implementation without changing the client. Now, in our television case, one of the ways that shows up is you might sometimes buy a new and better television, but keep your old remote if you happen to like your old remote. Back to programs. You've already met, of course, the idea of data representation in a few places. You know the idea that a data type is a set of values together with the operations on those values, and it may be primitive, it may be built into the language, in which case you'll have operations on the primitive data type which are defined in the compiler in the runtime, and you've already met in Java types like int and double and boolean, and we talked about the kinds of things you could do on ints and doubles and booleans and something about their semantics. For example, we talked about the semantics of division when you operate on doubles versus the semantics of division when you operate on other types. But you can also have user-defined data types, in which case the user, in this case the user is the programmer of course, can define the operations in the programming language itself. And we've started to see a few examples, printer queue and hotel room and so on, and you'll see many more. One slightly confusing thing about Java is that there's a whole kind of halfway house where things are defined in classes that come as standard with the library and with the language itself, and are so standard that learning Java includes learning how to use these standard classes. And the absolute most standard one is string, which we've already been using more or less as though it were a primitive type. And I think I remarked in an earlier lecture about how it was very significant that the word string starts with a capital letter there, in contrast to things like int, double and boolean. Well, the significance is that class names in Java start with capital letters and primitive types start with lowercase letters, and this is one of the mnemonics that helps you to keep these things straight in your head. It's worth saying, by the way, that the idea that a language comes with a standard class library, Java comes with the JDK, which has a vast number of useful classes, not only string but many kinds of collection types and user interface widgets and all kinds of things that you might need in standard programs. This is actually not an idea that was present with programming languages from the very start. It's one which has gained popularity over time. In the early days of programming, and even in the 1990s when I was first working as a professional programmer, you would have your language, which probably didn't come with a library, and then you would choose your library separately, and you might even have to pay for a commercial library to give you some very basic functionality, like collection classes. And that, of course, was a bit of a pain because it meant that you would be your code would be locked in not only to your choice of language but also to your choice of library, and there were problems if the library provider stopped developing the library and so on, or if it got out of sync with language versions. So these days, popular languages, generally speaking, do come with standard libraries, just like Java does. But that's a bit of a digression. So the point about hiding data representation is that you shouldn't need to know how a data type is implemented in order to use it. So this is an example of the kind of hiding of information behind an API that we were talking about. It should suffice to read the documentation. So you should be able to read some documentation, find out what operations there are on your data type and what they do, and go on from there. Now, key pieces of terminology which you will need to know, especially later on in your degree course if you do software engineering courses. This is my favourite sort of very brief definition of these two very common terms, abstraction and encapsulation. It's worth saying that the ways in which people use these terms are not completely standardised. You will come across people using these terms as though they were synonymous. You may even come across people using these terms with meanings that make them different, but not quite how it is here. But I think these are reasonably standard definitions. So abstraction and encapsulation are closely related ideas, but they're not exactly the same. So the idea is that you have a good abstraction of a data type if it's possible for you, when you are a client, when you're writing a program to use the data type, if you don't need to know about the implementation details. So it is possible for you to use the data type without going and understanding all the stuff that's hidden. And it's encapsulation if there's a mechanism in the language that means that you cannot depend on implementation details. Okay, not just you need not, but you cannot. Okay, so encapsulation is a stronger idea than abstraction. Java provides both. If you happen to know what this means, then this may be useful. If you don't yet, don't worry. You may have a good abstraction if you have a Java class which has a well-chosen collection of methods, but all its data, all its attributes are public. You've got encapsulation if you make the attributes private. Okay. Different languages have different mechanisms for doing this kind of thing. Now, so far in this course, we've been doing what's sometimes called procedural programming. So we've been focusing on control flow. We've been saying, how do you tell the computer to do this, and then tell the computer to do that, and so on. And you've learnt a bunch of stuff relating to this. You know how to program with primitive data types like int and boolean, and you know how to control program flow to do things with those primitive data types, like using if and for, and we talked a bit about arrays, so you know how to group collections of similar data into arrays, and I mentioned that there are many other kinds of collections in Java, but you haven't met those yet. The philosophy of object orientation, however, takes us a step beyond that, and as I advertised at the beginning of the lecture, the issue is that what your software must do changes a lot, and what we want to do is to try to structure the program based on something that will make it easy and cheap to make the kinds of changes that we can reasonably foresee. Now the thing is, the details of what your software must do change a lot, but the actual domain in which your software works changes much less, because it's usually much more closely related to the real world or to the conceptual world of some client, but anyway to something which is rather more stable than the details of the requirements of what your software should do right now. And this observation leads to the idea that structuring your software around the things in the domain makes it easier to understand and maintain your software. People sometimes talk about object orientation as being noun-oriented as opposed to procedural programming, which is verb-oriented, but I don't really like that characterization very much, because really nouns and verbs work together to make sentences, and so it is in object orientation. So the sense in which OO is oriented around objects is really to say that we use objects which are noun-like things in order to structure our software. Things in the world still have nouns and verbs. They know things and they can do things. And in Java, the things that something knows turn into instance variables, into data that is wrapped up in an object. And things that stuff can do turns into methods inside an object. It turns into behaviour of an object. So objects have state and behaviour. Let's get a bit more concrete. Here's an object. It's an object which is a car. It has state and it has behaviour. So some examples of the state that a car has are the Boolean, whether it's running at the moment, a thing in some kind of numeric type representing its speed, how much petrol it has. These things are all data about the current state of the object, and these things might change over time. Okay? It also has behaviour. It has stuff it can do. So if you have control over a car, you might be able to start its engine, stop its engine, accelerate, brake, and refill petrol, and so on. And notice that these things influence one another. Okay? So behaviour that the car carries out is very likely to change its current state. And similarly, its current state is likely to change what behaviour the car is currently able to carry out and the way in which it will carry out that behaviour if you ask it to do so. And these things are true in general of objects as well. So a program runs by means of objects sending messages to one another, and this is the way in which objects initiate behaviour, and by objects reacting to receiving messages. So a way in which an object might react to receiving a message is it might change its state, or it might send more messages. It might send a message to some other object. And one of the ways in which we've got information hiding, in fact, which we'll be spending a lot more time on later on, is that the way you should think about sending messages in object orientation is that the messages you send have names that correspond to the methods in your classes, and methods are very much like functions. But actually the way you should think about it is that the sender of the message does not know precisely what behaviour will be carried out when they send a message to an object. What gets done when the object receives the message is up to the receiving object in a rather fundamental way, which we'll see later on. But just hold that thought for now. So let's see a bit more about how this works in Java. So, terminology. Java is a class-based object-oriented language. What that means is that all code is organised into classes, and the classes serve as user-defined data types. And so here's a naive implementation of the car data type. We might arrange that the car has state arranged in those three attributes, a Boolean running, an integer speed, and a double of petrol, and it might have methods constituting its behaviour with those signatures there. So far, because we haven't written any instance methods, we'll talk about the difference between instance methods and class methods later on. All the classes you've written so far only define behaviour. We were always talking just about static methods, for example, the main method, which was where a lot of our code went. Although we did talk quite a lot about how to split up behaviour into smaller methods, smaller functions. One thing we haven't talked about yet is how you go about creating an instance of a class, an instance of your user-defined data type. And to do that in Java we need a constructor. So a constructor is used to create an instance of a class, and then having created an instance of the class, you can then use that instance, that object, in your program. It can, once it's been created, it can start receiving messages and sending messages and generally taking part in the program. So the constructor, it's a bit like a method, but it's a special kind of method. It always has a name which is the same as the name of the class which it's constructing. So here we have a single zero-argument constructor called car. So in this particular instance we've said invoking this car constructor should just construct a new car object, and you don't need any arguments to tell it anything about what kind of car to construct. That's all presumably has default values encoded in the constructor. Okay. Yeah, so I already said a constructor is a special method, has the same name as the class. What does it do? Well, two things fundamentally. It allocates memory for the class instance. That happens under the hood. You as the programmer don't need to worry about that in Java. although in some other languages like C++, for example, you might. And it initializes its state in an appropriate way. Right. Okay. So I've probably already been assuming that you understand this, but let me say it since it's on the slide this time. In Java, instances of classes are objects. Objects are instances of classes. So here's an example of the kind of code that we might write once we've got a car class with the API that I showed on the previous slide. We might do something like saying car, my car, equals new car. So this says now, okay, what I would like is I'd like to create a new object of class car, and I'm going to refer to my new object as my car. Okay, so my car is now, it's a variable name, it's a name which is going to refer to an object of class car. And the word car here is representing both the class with all the complications we've got, and also, as far as the type system of Java is concerned, it's a type. Okay, so to say that my car is a car tells you something about what things it makes sense to do with my car. For example, what messages my car will understand. So having got my car, we can then send it the message start engine, which requires no arguments, hence the empty round brackets there. We can send it the message accelerate with the argument 30. We can send it the message brake with argument 30. We can tell it to stop engine, and we can tell it to refill the petrol with argument 0.5, whatever that means. So a bunch of things, whatever is actually available in the API of the car class. So we have two almost independent, not sure they're really quite independent, ideas going on here. We have objects, such as my car, which are directly present in the program, and they have types, static types, that define their behaviour. Okay. Now there are actually other kinds of object-oriented programming languages that don't work like this. So for example, there are prototype-based object-oriented programming languages. But these days most of the object-oriented programming languages you're going to come across work fundamentally like this. They have classes, and then you create instances of the classes, and those are your objects, and the objects are the things in your program which exchange messages in order to get stuff done. So objects have a static, that is compile time type, which is defined by the class whose name you use when you create the object. They are instances of classes, they're created at runtime. And how do you create an object? You create an object using a constructor and the new keyword. Okay. They're reference types. Now what do we mean by that? Well, remember, we already looked at some of the peculiarities of what happens with arrays, and now what we're going to see is it's not peculiar to arrays at all, because very similar things happen with all objects in Java code. So we saw, for example, that we could have an integer array called myArray. We could create a new integer array by saying we want a new array of 5 integers. That's the first line there. And then we could set and read particular elements of that array using that square bracket notation. But the key thing we observed was that the name myArray was referring to a particular chunk of memory, at least conceptually. And so when we did things like passing myArray around as an argument to certain functions, because we were then passing the reference by value into our functions, that meant things like when we passed an array name into another function, it was possible for the second function to actually change something about the contents of the array. I hope you remember that kind of thing. You need to revisit the array lecture if not. And we had pictures like this at the time. Okay. Now this is very similar for objects. So here's a corresponding picture for my car. When we create a new car object called my car, what's happening is there's a chunk of memory allocated, and in that memory is stored the current values of the attributes of this object. So for example, the fact that the current value for the Boolean attribute running is true, the current value for the integer speed is 30, and so on. Okay. And then as the program proceeds, the values of those attributes that are stored in the memory that corresponds to the reference my car may change. So, creating a class instance reserves memory for its state, and it does a bit of extra stuff as well, which you don't need to worry about too much right now. The constructor gets executed and it initializes this memory. It sets it up with the correct set of default values. So you use new and the constructor in combination. And the local variable myCar, well, yes, it's local to wherever it's local to. It holds a reference to the actual object representation in memory, and this works the same as for arrays. By the way, this way of constructing objects in Java does have certain disadvantages, and if you do the course Software Design and Modelling later on, we'll have a lot to say about that. But this is the standard Java way to do things, and for most purposes, it's fine. Let's just finally emphasize the similarities and differences between class instances and arrays. According to the Java language specification, slightly curiously, these things both count as objects. So they're similar in the sense that they're both created using new, and they are referenced in memory, and there's an underlying class definition, although for arrays you don't really get to see that. It's hidden in the language implementation. They differ a lot. Some of these ways are obvious. So you've seen the square bracket notation for accessing elements of arrays, and there's nothing similar to that for classes. That's just for arrays, okay? A thing to be slightly aware of is that you have this special way of accessing the length of an array. You just go myArray.length. Notice no round brackets there, right? Don't confuse that with the fact that certain classes like string, for example, will understand a length message. If you have a string and you want to know the length of the string, you might go mystring.length and then a pair of round brackets, and that's a different thing, okay? That's not a special built-in aspect of the language. That's just the string class offering the length method as part of its API that allows you to get the length of a string. Okay, so people get those two things confused sometimes. So just remember this length thing as special to arrays. And obviously arrays don't have any methods in the standard sense that we're going to see. So arrays, classes, similar and different. What happens if we don't actually initialize our object by using new and a constructor? What happens if we write something like this? We could just go car, mycar.startEngine. Easy enough to do by mistake. Fortunately, this won't even compile. If you just write code like that, reasonably bare inside a class, you'll get a compiler error along these lines. It'll say something like variable mycar might not have been initialized. And indeed, in this code, it has not been initialized. So you can't send mycar a message because there isn't a mycar yet. Okay, no memory has been allocated for it. There's no new here, and there isn't an object that's being created. So we've declared that mycar is supposed to refer to a car, but we haven't created a car for mycar to actually refer to. So there is no car to start the engine of. So that's why this code won't work. The compiler is pretty clever these days at working out when your code is doing something silly like that, is trying to send a message to an object that doesn't exist, but it's not perfect. So if you do manage to fool the compiler into failing to notice that you're sending a message to an object that hasn't been initialized, then what you'll get is a runtime error, Java long null pointer exception. So this code isn't actually an example of that, because this particular error in this plain circumstance will be caught by the compiler, but it's worth actually thinking about the circumstances under which the compiler can catch those errors. It can't always do it. If it doesn't, you'll get a runtime error. So where do references point if there's no corresponding object allocated for them? If I say, well, okay, you told me my car wasn't initialized, well, what was its value then? Okay, so the answer is that to start with, its value is just null. Okay, and you can even set it to null. You probably shouldn't, but you can. And that's why we talk about a null pointer exception. It's because mycar is a pointer, effectively. It's just another word for reference, and it's currently null. It hadn't been initialized yet. So here's the difference. I think the point of this picture is the difference between being null and being empty, which is sometimes important. You can have an object which has sort of no interesting data in it because it's only got the default values or something, or you can have an object that simply doesn't exist yet. It's not a very good joke, is it? But hey. So all kinds of implications of this. One thing is that you have to be sure that you know what you're doing when you try to copy an object. So here's a piece of code that you might write. You might write car my car equals new car, and then you might say car your car equals my car. Now what's going on here? What we're doing here is we're saying the reference your car to a car object is set equal to another reference to a car object, namely my car. Now because what we're doing is we are setting those two references to be equal, what we're doing is we're saying those two references point to the very same car. Okay? And that has all kinds of implications. It means, for example, that if the state of this car that both of these references are referring to changes for some reason, then those changes will be visible via either of those references. Sometimes that's what you want, sometimes it's not. And this kind of copying, so assigning the reference of an object instance to a different variable of the same type, does not copy the object, doesn't copy the object's memory, it only copies its reference. Here is a manual way of copying an object instance so that you do actually get two different cars in memory that might ultimately end up having different state. We can create two independent car objects, and then we can in turn set each of their attributes to be the same as one another. So that's what this piece of code does. We've got two independent car objects, one referred to as my car, one referred to as your car, and then for each of the attributes we set the corresponding attribute of your car to be the same as the corresponding attribute of my car. So yes, that's about all there is to say about that. So how's this going to work? Let's check a few cases. So if we ask to print out the result of the Boolean expression my car double equals your car, what does this print? It prints false, because the double equals comparison between two objects is checking whether two objects are the very same object or not. And the whole point here is that they're not the very same object. They may happen to have the same state, but they're different objects. They have the potential to be different. So double equals compares object references, doesn't compare object states. Okay. If we do what we did in the first example, which is to say we only create one car, and then we declare a new reference to it by copying over the reference, and then we ask whether these two things are the same using the double equals, then we do get true, okay? Because here there's only one car, and both of these two references are references to the very same object, and that's the thing that double equals is checking. If we have two cars which have been created in the same default state, and then we check whether an attribute of each of the two things which has primitive type are equal, then we are going to get the usual comparison that you've seen before for primitive data types. In this case we're going to get true, because that int 30 is equal to the other int 30, and you can check that using double equals in the way that you're familiar with. Sometimes that doesn't give you the information that you're interested in. Sometimes you really would like to know, given two objects, do they have equal states at the moment? You might say, I understand that they might not be the very same object, but are they in the same state at the moment? And to do that you use equals, which is more flexible. Okay. So most Java library classes have sensible implementations of the comparison method equals, and here's one example of its use. We can define 3 strings, one containing hello followed by a space, one containing world and one containing hello world, and we can ask, is it the case that A plus B, remember plus works as concatenation on strings, is that equal to C? And the answer in this case is yes. You'll get true printed out as a result of that. What's going on here, by the way, is that the equals message is being sent to the object C with the argument being an object which is the result of doing A plus B. Okay? C carries out the behaviour, which is to say, I'm being asked whether something equals me, and the thing I'm being asked whether equals me is this thing called A plus B. This thing which is A plus B. It's not that it's called A plus B, is it? And we'll talk a bit more later about what the equals method actually does. That's a good place to stop.